Thank you. I'm assuming everybody uses GPS or navigator when driving the vehicle, right? Anybody uses Tesla FSD, full driving suite there, which essentially takes the control from you and then follows the GPS points to your navigation points. So let's see if this video runs. Okay, this is the last week video where I personally experienced, so, okay. I'm personally over this spot and this GPS is telling me I'm on the road and it turns on my driving mode on the phone. Like it continuously telling me that I'm, okay, I've cut the video, but it's not showing, but it's showing me on the highway while I'm sitting in my room, okay? So this GPS issue sometimes becomes real, and especially when you're driving or if the vehicle is following the GPS points itself in navigation, this issue is real. Some of the experiments that we did in, this is car lot, CARMEN parking. If you have GPS jamming, which we did somehow, we were able to see how much position error we can see. The blue lines are the actual spots or points where we drove the vehicle. If we have GPS error, we can see vehicle thinks it's driving somewhere else. So this all brings the question to, if we don't have the GPS, what do we do? How do we make the vehicle follow or first localize itself and then follow the path or navigate through the designed or designated path? This activity is part of DOT's funded UTC. I'm one of the PIs. There are, I think, 7, 8 PIs working on different topics, but CARMEN is a good acronym. In OSU, it means other things also, but outside of OSU, people also confuse, okay, CARMEN goes to the canvas. What is CARMEN? So CARMEN is essentially Center for Automated Vehicles with Multimodal Assured Navigation. How we can use multiple sources on the board, on the vehicle, to localize the vehicle and then navigate the vehicle. Yeah, I'm part of Center for Automotive Research. I'm assistant professor in mechanical engineering also. So this is the overall picture of the CARMEN project. There are a lot of aspects when we are looking at the vehicle localization issues, from the GPS sites, which other PIs are looking into, to cloud and edge data sharing that vehicle needs. There are people, other PIs looking into. I sit in the vehicle where I'm using the cooperative sensing and other sources of information to localize the vehicle, and then using other signals of opportunity. So we have cellular signals, we have V2X signals floating around, which vehicle can use to localize itself. And then we have onboard sensors. So this is an onboard modality that we can use to localize the vehicle. Now, when it comes to autonomous vehicle stack, there are a lot of things going on in the stack itself. We have sensors, camera, LiDAR, GPS. This is particularly we are using. There are more than these sensors. These sensors are used for perception, perceiving the environment, and then localize the vehicle where it is on the map. And then planning layer, controls layer, and actuation layer, they use this information. But if you see, localization sits just after the sensor, and this information is heavily used in planning and in controls and in eventually actuating the vehicle. So any solution that we or I will be talking about will sit in this block of the overall stack. Now, with this stack, we ran this vehicle. We have to follow, let's say, S curve over here. It has to follow the GPS point, so GPS is enabled. When we disable the GPS, you can see this car in motion on weekends if you are on the campus. So when we disable the GPS, what happens is instead of following the path, it starts to circle around um, uh, the GPS coordinates that was last received by the vehicle. So essentially, it doesn't follow the command that it needs to. Then we enabled it, and then it got back to the track, and so we were able to follow the path. Now, with all these evidences, essentially, there is a need of non-GPS based localization, that we need to have that alternate. And especially lane level accuracy. We want to maintain the lane level accuracy because GPS enables us that. Typically, lanes are 4 meter wide. If you're in the lane center, then you have 2 meter right, 2 meter left sort of accuracy that you need to maintain. So sub-meter or sub-2 meters accuracy is important, even if you're looking at other modalities for localization. GPS inaccuracy, maybe when you are going through the tunnel or you are within the downtown, you see signals bouncing around, right? So GPS accuracy is a question also. So when we look at the solution, non-GPS based cooperative localization, meaning you don't use GPS, you use other sensors, and sometimes you just use non-cooperative localization. Essentially, you build a network around the vehicle to localize yourself. So there are efforts, people have been doing this. For example, using roadside units. These are the vehicle-to-vehicle communication or vehicle-to-infrastructure communication devices. They are using time of arrival, signal time of arrival to locate themselves. LiDAR-based SLAM, so it's onboard sensing capability. Map-based visualization. So essentially, we know the map or Google Map or any map is available and we can download it and we know the coordinates or let's say lat long values of our path that we need to follow. So we can use that also. A lot of efforts have been done on the network side, radio navigation. So you receive a signal, you broadcast a signal. Based on the signal strength, you try to localize yourself. Sensing based approaches are also common. Depth reckoning is where you bring in the vehicle dynamics. Practically, it's not possible for the vehicle to change a lane all of a sudden, right? So there is some vehicle dynamics that play a role over there. So that reckoning takes into account some of the vehicle dynamics pieces into the localization. So when we are dealing with network-based solutions, we know when using our phone or data on our phone, network is not always reliable. So on the vehicle, we cannot go behind network-based solutions. Camera and LiDAR-based solutions, they bring in, so for example, Tesla's solutions are all camera-based. They are most of the times, let's say they are good, but there are always edge cases where camera can fail. Hence, LiDAR comes into the picture, but LiDAR is expensive. We have to process all this information. A lot of companies, for example, if anybody is using Super Cruise or Ultra Cruise from GM or Ford, their solution is dependent on HD map. What is an HD map? Let's see if this runs. Okay, this is not running, but HD maps are more than what we use in the Google map. Essentially, in the HD map, I have all the lane markings. I have the 3D point cloud data, meaning that I have the lat long values of any static obstacle of the map that I have already mapped. So there are companies who provide HD maps with all this detailed information. And hence companies use this HD maps to localize themselves because the buildings remain the same, road remain the same, lane marking. So that gives them some sort of ground truth. But imagine you have to maintain this data set for the whole country, right? So this is only available for few portions of the cities even. For example, Detroit will have some, there are a few other cities that they have the HD maps. So again, use of HD maps, other sensing, they have their own challenges. So, and when we are using the dead reckoning approach, there's a drift. Lane level accuracy is very important. And then a lot of things depend on the expensive infrastructure, for example, V2X infrastructure. So we need to have a solution that somehow gives us cheaper option, but gives some of the similar capability. So what we started looking into 2D maps. This is available to us through multiple sources. V2X devices are also announcing this 2D map. We have Google Map, we have a navigation within the infotainment system. So this information is already there. So this gives us the ground truth. If we know the coordinates of the map that we would like to navigate, we can divide it into segments and then start using that as a ground truth. Then we use vehicle dynamics over here. So some of the simple kinematic model for the vehicle. Okay, we know that if the vehicle is following the straight path, it cannot all of a sudden change its lane. So vehicle dynamics give us some information that we can build on. And the last piece is we used arc length based method to eliminate the error that dead reckoning, which builds on the vehicle dynamics. We use map and the vehicle dynamics in parallel or in the arc length based approach to cut down on the error. How does it cut down? For example, if we have this dead reckoning kinematics model, this gives us an error. Right? At this point, we lost the GPS point, and this is the ground truth. This is the map information we are getting from any source. So we have this piece, we have last location where the GPS was lost, and we have some sort of kinematics model with us. So what we do, we use vehicle kinematics. It will have some drift in it, but we correct it and bring it back because we have the 2D map information with us. So this was a very simple approach. Okay, we see how much we drifted, we compare it with the 2D map, we bring it back on the map, and hence we keep on our we keep the vehicle on the route. So I will have no maths in my slide. If you want to see maths, we have papers on that. So anyway, so with this, we divide the, let's say, route in segments. We keep on correcting ourselves. And then eventually we are able to maintain the lane level accuracy, even if we don't have the GPS. Now, whenever we talked about this solution with the automotive company, they say how many scenarios you have evaluated. We have evaluated, for example, 20 scenarios, but they are saying, no, you need to evaluate more. Where it fails, we need to find that. So when it comes to the testing process, we first do simulation testing, then on the track testing, and then on the real world environment testing. We did some of the simulation testing. You saw some of the, let's say, closed track parking testing. We cannot say track testing, but we are doing that also. Real world testing, it's a big question, so I don't know when we're doing it. These sort of scenarios we look into. So there are certain scenarios, for example, if you're going straight in the path, that's an easy way to handle because it's all straight. But when you have four-way intersection, T intersection, Y intersection, things get challenging over here. So for all these scenarios, we evaluated this approach. We needed to have the ground truth. So we had GPS, not to aid our algorithm, but to give us the ground truth. Now, this GPS itself gives us centimeter level of accuracy, 5 centimeter, but this is like a $25,000 GPS, which is very expensive for anybody to have, right? But we want this level of accuracy. If we can replace this GPS also, that would be great. So, and then we use some of the data that we were able to access through, in the vehicle through CAN. And then we had 2D maps of the different scenarios that we evaluated. These were the signals we recorded. We were able to access to the CAN and then actuate the vehicle through the CAN, so which means we need to operate within 10 hertz. So we should be able to calculate everything. and execute everything within 0.1 second. So this is one of the first scenarios. So we have kinematic model, meaning that dead reckoning approach, ground truth with the GPS and map matching. Now, if you observe over here, when the kinematic or dead reckoning approach, for 10 seconds, it's good. For 20 seconds or 30 seconds, as we keep on driving the vehicle, the error keeps on accumulating. That's the typical problem with the dead reckoning or kinematic based approach. Whereas map matching, which we are proposing, keeps, yes, there is 0.8 meters. We are still sub-meter level of accuracy in this scenario. But overall, if you see, dead reckoning and map matching are going good in this scenario. And in some cases, for example, you see we are 1.6 meters, and then, kinematic model is 1.6, we are 0.6 meters. But in Y coordinates, kinematic model is better than ours. So we are trying to find out where we can better rely on kinematic model versus map matching, and hence we have multimodalities on the vehicle. We evaluated some other scenarios, so left turn, similar analysis. Over here, if you see, we have like more than 3 meters of error. So we are trying to find out how we can fix this, but in x-axis or in x coordinates, we are around a little over than 1 meter. But in some scenarios, for example, this is a left turn with, I think this is T intersection, right turn. Yeah. So you see kinematic model, it totally takes you to a different lane. Whereas our algorithm, when it compares to ground truth, yes, there is some error, but we are still following the right lane. So we have the lane level accuracy with us. Similarly, we kept on evaluating different scenarios. We ran around 14 scenarios that we have results over here. We have to keep on testing this, see where it fails. But overall, what we are observing, our error remains within, let's say, 1 meter or at least 2 meters of accuracy, which is the lane level accuracy which companies are looking for. And we are not using HD maps. We are not using any onboard sensors. It is just the 2D map that we can download on the vehicle, or we have access through our, let's say, navigating apps. Now, I'm not claiming that this solution will work for all situations, right? So where are the limitations? We are assuming that we are always in the lane center. We have 2 meters on the left, 2 meters on the right. So this is our initial condition. So how do we avoid it? We are looking into this. Then lane change, when vehicle has to change the lane, we are going beyond the lane level accuracy. So we need to inform the algorithm, yes, it's a lane change, so don't worry about it. So that's an additional capability that we would like to look into. And we have dependency on the map, 2D map over here. How the level of accuracy will determine our level of accurate solution also. So these are some of the dependency or limitations that we are dealing with. But overall, I think we were able to crack into the GPS denied navigation. We improved the solution on top of the dead reckoning that adds to the safety and reliability. The algorithm takes 3.3 milliseconds to take over when GPS is blocked or jammed. And it takes 10 milliseconds to 700 milliseconds to calculate itself. So we are well within 0.1 seconds of computation time that we need to have on board or on the vehicle. So this implementing things online and testing them, this is the team that we have working on this. So it's not one person's job. So thanks to all the students. And with this, I would like to thank you. Any questions, or I think I won't step between lunch and you guys. Okay. Yeah. So yes, it's a supervised autonomy, meaning that There will be a person on the steering, but not, we are not controlling the steering. So it is autonomously moving. So that was on the street. We gathered, so with the parking lot, what we are doing is we map those scenarios and make vehicle think that we are in that scenario in the parking lot. So we are fooling the vehicle over there. Okay, because we cannot do these testing on the actual roads. So we create these scenarios in the parking lots, and we can mimic the same situations over there. Okay. No. So that's the radio or network-based navigation. Yes, there are people working on it, but we are not relying on a network, because network itself can be somewhere it's very good, some places it's not good. So, but that's again, when we call it signal of opportunities. So apart from GPS, you have other signals to localize yourselves, but we are not using that right now. Okay. Okay.